Welcome to Lecture 2. Lecture 2 will be in two parts so that each recording is not too long and a little bit more digestible. So in this first half of Lecture 2, we will talk about descriptive statistics and probability and how probability ties back in with statistics. So first, where does data come from? So if you remember from lecture 1, Dr. Armenta talked about population versus a sample. So a population is a complete collection of observations or potential observations for all individuals or units of interest. And this is defined by the investigator. And if you remember, oftentimes we can't study an entire population, both for practical reasons, and resource-wise, it's just not possible in most situations. A population can be very targeted. So for example, we might be interested in competitive bodybuilders, or it can be very broad. So we can define our population as anyone who lifts weights at least 2 times a week. A sample, on the other hand, is a partial set of observations taken from that population. And so by and large, most of the studies we do are on samples of a population of interest. They're typically much smaller than the population. So for example, a study might include a sample of 50 weightlifters. And then as a comparison group, we might also include a sample of 500 sedentary individuals. Our sample ideally is representative of the entire population of interest. And it's not always the case, but that is ideal. And then many samples can be taken from a single population. So a little bit of terminology. A statistic is a measure from a sample. So for example, the average height of 100 CSU San Marcos students, whereas a parameter is a measure from a population. So for example, the average height of all people in San Diego. So we often don't know what the value of these parameters are. And so what we're doing is we're using sample statistics to make inferences about population parameters. So what does that look like? Let's say, for example, we're interested in the population of 2.4 million adults in San Diego. And the population parameters, in this case, we happen to know the average height is 66.5 inches. And of all the adults, 48% are male and 52% are female. But let's say we take a sample of 100 people from this population of interest, and then we measure their height and we ask them whether they're male or female. So in this first sample of 100 people, our average height is 64.75 inches, and there are 43% male and 57% female. And then let's say we take another sample of 100 people and we measure their height, and we get an average height of 67.25 inches. And then we have 51% male and 49% female. And so you can see these values between the samples are a little bit different, and they are still also different from the greater population, but somewhat similar, right? In real life, we generally don't know the true value or the values of these parameters. And so what we're doing, again, is we're taking samples from the population of interest and trying to estimate these population parameters. So what are some examples of descriptive statistics that we can use to characterize our data? Another note too is that this portion of all of our research is probably the most important. So it can seem very boring to spend the majority of your time really exploring your data and understanding what it looks like, but it's really important because this then drives the type of analytic approach that is appropriate for your data. So one way that we can depict our data is through frequency distributions and histograms. So a frequency is really just how many times an event or observation occurs. And then a distribution is just sorting those observations into classes or categories and then displaying the number of occurrences within those classes. It's a great tool for representing and ordering your raw data. And you've probably seen one example of a frequency distribution before, so that's a histogram. So a histogram is just a graphical display using a bar type chart, and it shows the frequency of particular events. Another way that we can display a frequency distribution is with a table. And so in a table, we would just sort our data within classes and then display the number of individuals or number of observations that fall within those classes. And we refer to that as a contingency table. So what does this actually look like? This is a very simple example. So let's say we have a collection of coins, and what we would want to do first is to divide our observations, our coins, into classes. And there are only two classes possible, right? So heads or tails. So we have this collection of coins, and then we want to count the number of times or the frequency of events in each class. So let's sort our coins. So here on the left-hand side, we've lumped our coins with tails on one side, and then we've lumped our other coins that show heads on the other side. And then we count the frequency of events in each class. So here we have 8 coins that showed tails, and we had 5 coins that showed heads. So it's a very simple example of a frequency distribution. But what does a table and a histogram look like if we were to do something like this? So here we have a sample of 79 individuals who swam 100 meters. In this left-hand column, we have each class. So this is 60 to 64 seconds. This is 115 to 119 seconds. So here we've just taken the times for the 100-meter swim and categorized them into these different classes. And then within each class or category, we also have in the second column the number of individuals that fall within that category. So for example, within the class 85 to 89 seconds, we had 17 individuals complete that swim. So they fall within that category. And then that corresponds to the bar here on the histogram. So if we kind of break this histogram down a bit, on the y-axis, we have the frequency, so the number of individuals who fall within, and then on the x-axis, we have these individual classes. So these are the number of individuals who fall within these individual categories or classes. And so you see here the 17 individuals falling within that class, and that corresponds nicely to this bar right here. And similarly, this bar corresponds to the 2 individuals who fell within that class, so that time of 60 to 64 seconds. So if you notice from our distribution, it looks like a bell curve, right? Not perfectly, but it's a nice little bell curve. So in all distributions, there's this central tendency, and that means there's a central or typical value for a distribution. And when we have a normal distribution or distribution that is perfectly symmetrical, our mean, median, and mode are all the same. And if you remember from lecture 1, the mean, median, and mode are all measures of central tendency. Right, so the mean is our average. The median is the point at which 50% of observations fall above that point and 50% of observations fall below that point. And then the mode is just the most frequently observed observation. So our distributions can be normal, like this graph here, or they can be skewed. So if the tail of a distribution is pulled to the right, as we see here, so it's like stretched out to the right this way, we call that positively skewed. And in this case, the mean is greater than the median. And if you remember, the mean is very much affected by values that are extreme. So it's just pulled to the right this way. In contrast, if we have a distribution that is pulled to the left, then we say that distribution is negatively skewed. And in this case, the mean ends up being less than the median. So skew is just one property of a frequency distribution. And again, a positive or right skew means that the scores are all bunched at low values with the tail pointing to high values. So it's stretched to the right. And a negative skew or left skew is one in which scores are bunched at high values with the tail pointing to low values. So again, stretched to the left. Another property of frequency distributions is kurtosis, and that just refers to like the heaviness of the tails. So in a leptokurtic distribution, we have heavy tails and observations are all clustered at the center. So it looks something like this. And you can see the tails are a little bit fatter. And then in a platykurtic distribution, we have light tails and observations are more spread out. So they're flattened out a little bit. And you can see the tails out here are much thinner. So if you remember, Dr. Armenta mentioned that a mean is a very important measure of a sample. It's a measure of central tendency, right? And it's something that we see a lot. But that doesn't tell us the whole story about the distribution of our data, right? So what if we have two samples of individuals and both of them have a mean height of 65 inches? And so then we might conclude, oh, well, you know, they're pretty much the same. But it's possible that there's a lot more variability in one group versus the other. So what is variability? Variability is the degree to which scores in a distribution are spread out or clustered together. So how much are the scores alike? Or in our previous example, you know, how close together are the height measurements? How much of a difference do you expect in your scores? Are they really spread out? And so there are large differences between individuals. The lower the variability or spread, the better the mean represents the entire distribution. And so what that means is if we had an average of 65 inches in our first sample and 65 inches in our second sample, but in the first sample, there's a lot of variability, the mean might not be a good representation of that entire distribution because not a lot of individuals are close to that mean of 65 inches. So here's one way we can look at that. So let's say we have here a graph A and measures about that central tendency, and we can kind of imagine that this line is the average. And then we can compare that with graph B. So which one has more variability? We would say this second sample, right? Because all these points are really kind of spread out and away from this average here. Another way we can look at that is by looking at a distribution this way. So again, we might have two distributions that share the same mean. So in this case, there's a mean of 50 for both of these curves, but the red distribution has greater variability, so it's much more spread out. Whereas for this blue distribution, the scores are really clustered around the mean, so more values are going to fall closer to that central measure of 50. What are some other measures of variability? So another measure might be the range, and that's just the maximum minus the minimum. So it would be the maximum value minus the minimum value. And these are radically changed by outliers, and we'll talk about outliers a little bit later in lecture 2. Another measure is the interquartile range. So the quartile is just when we've divided all of our observations into even groups, four groups. So we have our first quartile at the bottom, second, third, and fourth quartile at the top. And the interquartile range is just the difference between the 75th percentile and the 25th percentile. So this shaded area here. So it's the middle 50% of our population. So which is always larger, the interquartile range or the full range? The full range, right? Because that goes from the minimum to the maximum, whereas the interquartile range is just that middle 50%. Okay, so what we're getting at is really one statistic that we often measure in our samples, and that is the standard deviation. And that is the most critical measure of variability of observations in a distribution. And it really tells us a little bit more about our data than just something like the mean. So the standard deviation is the typical or standard amount that scores differ or deviate from the mean. Unlike the range, the standard deviation uses all observations to quantify the spread or the dispersion of the scores. And the standard deviation is very, very important in inferential statistics. So we can calculate the sample deviation, but that allows us to estimate the unknown standard deviation and variance in a population. And you'll see why that's important when we start to talk about hypothesis testing and running models for our data. So what is the variance? I mentioned that, right? That we can use the standard deviation to estimate in our sample to measure the standard deviation and variance in the population. The variance is just the average of the square deviations from the mean. So this might look familiar to you because we looked at it in lecture 1. So the formula for variance of a population is the sum of squares. So each observation minus the mean squared, and then we add that all up divided by n. Okay, and that's something that we can estimate, but we don't know. So in our sample, the formula for variance is the sum of squares. So the value for each individual minus the mean squared, and then we take the sum of that and we divide it by our sample size n minus 1. And this looks familiar because we looked at standard deviation in lecture 1, and the only difference is that it was the square root of this expression here. So remember, if we don't square the difference, then the sum would be 0. Okay, why do we divide by n minus 1? So a sample will be biased based on which individuals are selected. So remember, ideally we would select a random sample, and that sample would be representative of everyone in our population of interest. But that's not always the case. We assume that the mean of the sample represents the mean of the population, even though our population mean is unknown. So therefore, that last data point in a sample can only be one value, and that one value will make the sample mean equivalent to the population mean. All other values are free to vary, and that is called our degrees of freedom. So that last point, that minus 1, that last point is not free to vary. There needs to be one value to make the sample mean equal the population mean. Therefore, we divide the sum of squares by n minus 1 and not just n. So again, the degrees of freedom is the number of values in a data set that are free to vary. And as our sample size increases, the degrees of freedom also increases, and the sample standard deviation becomes closer and closer to the population standard deviation. So we'll go back over again standard deviation, and we'll do, I know Dr. Armenta did a quick calculation in lecture 1, and so we'll look at another example. So in the left-hand column, we just have 10 individuals, and in the right-hand column, we have the number of hours of sleep for each individual. Okay, so this is person 1, and the number of hours of sleep was 6. How much variation on average is there in this sample? So we'll take our formula here. First, let's take each observation minus the mean. So the mean is 5. right? So all the hours, we've totaled them to 50 divided by 10 is 5. So the average sleep for this group of 10 individuals is 5. So for this individual, their hours of sleep is 6 minus 5 is 1. And then we square that and we get 1. So we repeat that. 2 minus the average, which was negative 5, which is negative 3. And we square that and we get 9. So we do that for all of our individuals in the sample, and then we sum that up to get 30. Okay, so our variance is just the sum of squares. So that's 30 divided by n minus 1. So our sample size is 10 minus 1, that's 9, and we get 3.33. And then the standard deviation is just the square root of the variance, and so we get 1.83. So oftentimes when we report data, we're not just going to give something like the mean. We also give the standard deviation, and that's just to give readers an idea of how much variability there was in our sample. So for example, we might say in our sample, the height of the class was 67 plus or minus 4 inches. What if our data is skewed? So if you remember from the distributions that I showed where there was a normal distribution in the middle, and then we had on either side a skewed distribution, and we saw that the mean was stretched towards the tail. So if it was positively skewed, the mean was stretched towards the right. And if it was negatively skewed, the mean was stretched towards the left. So when we report the mean, we're really assuming that our distribution is somewhat symmetric, and so that it is a good measure of central tendency. But if our data is skewed, that might not be the case. So here's a great example. So for ratio or interval data, the mean is often an appropriate measure. But let's look at how this example, how the mean looks when we look at this entire sample. So here we have 10 students, and each student has a mark, let's say on an examination. So this student 1 has a mark of 35, student 2 has a mark of 40, all the way to student 10 with a mark of 93. If we were to take a mean of all of those examination marks, it would be 46. But as you can see, most of the scores are actually less than 40. The reason for this is because the data is skewed. So the assumption is violated for interval ratio data, and the mean is actually not a very good measure of central tendency for this particular data. So again, this is one of the reasons, this is like a great demonstration of why it's so important to understand what your data looks like before you report statistics on it and before you proceed then to doing your analyses for those data. So in this case, because our distribution is skewed, that assumption is violated, and the median is actually a better option because the median is not very much affected by extreme values. Here, the median for this small sample of 10 students is 35, and that is a more representative score. So you can see more of the values kind of center around that median value of 35. Okay, so let's talk about probability. When we think of probability and statistics, we know that they're very closely related. And in fact, statistical inference is built on top of probability theory. But they are different. So probability tells us how often different kinds of events will happen. Questions in probability start with a known model of the world. In probability theory, the model is known, but the data are not. So remember, there's some truth out there, and we're trying to get at that truth. So statistical questions work the other way around, right? In statistics, we don't know the truth about the world, and that's actually what we're trying to figure out. All we have is data, and we're using this data to learn the truth about the world. Okay, so to kind of reiterate, probability theory tells us how often different kinds of events will happen. So the probability of an event E, let's say, is the proportion of times that a particular event is likely to occur. And that's used as a measure of the likelihood of the occurrence of some event relative to all other possible outcomes. And probability ranges from 0 to 1, or if we look at it as a percentage, from 0% to 100%. So it just looks like this, right? The probability of event is the number of those events out of the number of all possible outcomes. So for example, the probability of heads in a fair coin toss is 0.5. So some questions in probability might look like, what are the chances of a fair coin coming up heads 10 times in a row? Or what are the chances that I'll win the lottery? So all of these questions start with some model of the world that we can use to do calculations, as we did with the probability of heads, right? In statistics, we don't know the truth about that world. That's what we're trying to figure out. So statistical questions might look like the following. If my friend flips a coin 10 times and gets 10 heads, are they playing a trick on me? So we know that they've flipped the coin 10 times and we observe what that result looks like. And now we're trying to make an inference or a decision and say, well, are they playing a trick on me based on those results? Another question might be, if the lottery commissioner's spouse wins the lottery, how likely is it that the lottery was rigged? So we base our decisions on the data we have to make inferences about the population or the truth or the true probability. Descriptive statistics provides a factual information about observations from our sample. And then to go beyond those observed facts, you need some basis for making an inference about population parameters that are unknown. An inference asserts the probability that an observed fact in your sample is true for the entire population. And so this is how probability and statistics relate to each other. And I'll try to give a few more examples to kind of help this all connect together. Before I do that, I want to talk about two views of probability. So by and large, the most popular view is the frequentist view of probability. And that defines probability as a long-range frequency, and that only repeatable events have probabilities. So remember, probability is the number of times an event can occur over the number of all other possibilities. So what does long range mean? That means, for example, if we flip a fair coin, the more times we flip a coin over and over and over again, the more likely you are to end up with the quote correct answer. So if we flip a coin, let's say 5 times, 10 times, 100 times, eventually that that frequency that we observe should start to approach 0.5. In the frequentist view, the population mean is real, but it's unknown, but we can estimate it from data. So let me try to give an example of these, the second and a third point. So what's the probability of a coin toss? All right, so P, the long run proportion, it's the probability of an event occurring over the total possible outcomes. And we know that for a fair coin, the probability of heads is 0.5 and the probability of tails is 0.5. What's the probability of tossing 2 heads in a row? So if we toss a coin and we see heads or tails, that's independent from a second coin toss in which we can observe heads or tails. So we just multiply those probabilities together. So P heads 0.5 times P heads 0.5, and we get a probability of 0.25. So the probability of tossing 2 heads in a row is 0.25. All right, so sticking with that example and then looking at how the observation in our sample eventually approaches the truth as our sample size gets larger. We can see this actually with the Super Bowl coin tosses. So let's just look at this first column here. And these are the results of the coin toss for the Super Bowl in 1967 all the way through 1982. So let's count the number of heads. So we had 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 times we observed heads. Okay, and then the number of tails, 1, 2, 3, 4, 5, 6, 7. So within these Super Bowl years, we had 9 tails and, 9 heads and 7 tails, right? Pretty close to 0.5, but not quite. But when we look at all years from 1967 to 2014, so many more observations, our sample size is larger, we actually come up with exactly 24 heads and 24 tails, right? Perfectly 0.5. So what's another way we can look at this? If you look at these 4 graphs, these are just 4 simulations. So on the left-hand side, it's the proportion of heads. And then on the x-axis, we see the number of flips. So you can see, at least in this trial, when the number of flips is still quite small, the proportion of heads is pretty erratic, but still kind of centered around 0.5, right? Which is our true value, our true probability. But you can see as the number of flips increases all the way up to 1,000, now it's all converged to this true value of 0.5. And you can see the same thing happening in the second, third, and fourth simulation. So in contrast to the frequentist view of probability, there's also a Bayesian view of probability. And this is not as popular, but it is gaining a lot of traction, especially in particular disciplines. So Bayesian view of statistics, we can kind of view it as a subjective probability. So it's the probability of an event happening, the probability of an event happening is the degree of belief that a statistician assigns to the truth of that event. So in Bayesian statistics, probabilities don't exist in the world, but rather in the thoughts and assumptions of people. And it's very data-driven. So whereas in the frequentist view, we have a population with some truth, and we're trying to estimate that with our sample, a lot more value is placed on samples in Bayesian statistics, and it's very much data-driven. And we're constantly updating our probabilities based on what we observe in our samples. So what's some real-world application of Bayesian statistics? So for example, if you're watching Netflix and then it suggests shows that you might be interested, that's based on shows that you've watched in the past. And as you watch more and more shows, there are algorithms, there's like a machine learning process behind that that's gathering that information and analyzing it and then making new suggestions to you on Netflix. So this is very similar to, for example, if you're shopping on Amazon and Amazon suggests items that you might be interested, and a lot of times this is going to be dependent on items that you've viewed or purchased on Amazon before. And ads on social media is another example of this. So everything is kind of updating as time goes on and more data are collected. But in this course, we will focus, everything we learn will be based on the frequentist view of probability. And you probably won't see in kinesiology research, by and large, any application of Bayesian statistics. But again, it is gaining some traction. I know, for example, in genome-wide association studies, this is a very popular approach for analyzing those types of data. Okay, so let's try to make the connection between probability and statistics. Remember, they're different, but kind of they're very much related. They both concern themselves with analyzing the relative frequency of events. But probability describes the likelihood of a future event, whereas statistics describes the relative frequency of a past event. So the inferential leap comes from interpreting probability as providing an expected relative frequency of an event in the future random sampling from the population. So what does that mean? So let's say we have, again, going back to this example that we showed in the beginning of the lecture, we have 2 samples, each with 100 people from a population of adults in San Diego. And in our first sample, we have 43% male and 57% female. In our second sample, we have 51% male and 49% female. And what we're trying to get at is, how do we know if these sample statistics differ from the true population parameter? And in this case, although we know the truth, often we don't know the truth. And so we're relying on probability, the truth, or the expected probability or likelihood of a specific observation. So what's the likelihood that we'll have the probability of being male is 48%. In truth, we're wanting to estimate that with our sample, and that's where that inferential leap is. How do we do that if we don't know the truth? And that's what we'll start to talk about in the second half of lecture 2.